All right. So today's class will be about one topic, and that is radiative diffusion. Okay? So, in our description now of the specific intensity as our main macroscopic quantity and the radiative transport equation as the main equation that we normally solve in order to get our information. We dealt the last time typically then with some sort of system. We have a medium here, gaseous medium, and then we talked to some extent on how if we're an external observer, then the radiation, if this is a very opaque medium, that we actually see is essentially from around these layers with an optical depth of unity, right? These are opaque layers that we cannot essentially observe directly. We're forced to use indirect methods if we want to study them experimentally, that is observationally. But there are also instances where we need information about these very opaque layers in order to build up a sufficient description of the astrophysical system. Okay? Now, if we think about this layer here as some sort of boundary layer, we can call it, separating the opaque interior with the essentially free-streaming limit up there, then of course this represents something like material which has an optical depth much, much greater than unity. But of course, if we take the most classic example for an astrophysical system, a star, then we know that the energy is generated in the core, nuclear fusion processes. But then it gets, of course, transported all the way from the very opaque core to the surface, and then it escapes to us. We see the stars. We see our sun. Okay. So the energy has to go out from this all the way to this boundary layer, even if we cannot see it. So if energy then is transported by radiation, it means that it cannot be in complete equilibrium, because then we know the flux would be zero. It would be Planck body and it would be isotropic. So we have to have small deviations from this. Yeah? And I'm saying now that we're neglecting alternative modes of energy transport here. That is, if you have enthalpy advection, so-called convection, that is not the topic for today. Today we're going to look at the radiation part for this opaque medium. And it turns out that this can be very well and conveniently described as a diffusion process. And this diffusion process then is actually the photon equivalent again to the matter diffusion, or as it's often called when you study, for example, in your PDE course or in mathematical physics, the heat equation. And we will come to that description later, as derived also from a random walk, in this case, of photons. Okay. I will just make one remark before we begin, and that is that when I say that tau equals to approximately 1 to surface, that represents our boundary layer, where this is not a good approximation, the diffusion description that we'll do today, I neglect the potential issue of scattering. Now, scattering in this, remember we talked about this, that you can have absorption and emission, and that means that essentially the radiation gets absorbed by the gas, and then of course it delivers energy to the gas, then can be re-emitted, so the matter can re-emit, deliver energy to the radiation field, and then we have an exchange there. Now, of course, if we have scattering instead, so for example, I have, I don't know, a free electron here, as we will look at, and then we have an incoming ray of radiation or a photon, and then it's just scattering off here. Then it's not necessarily any energy exchange between the material and the radiation field. There can be momentum exchange, but not necessarily any energy. And that complicates this picture quite significantly, because you can easily imagine that then it can mean that, you know, photons can be scattered essentially from here and preserve the properties of the material from deep down here, where the optical depth is perhaps greater than unity. But if they were emitted and then just scattered around here and escaped, then they reflect the material properties down here and not from tau equals to 1. That's a complicated, and we will simply ignore that for today. It's just a word of warning for you. Now, all right, let's go now to the diffusion approximation, starting then with, again, our standard description now. And this is our complete radiative transfer equation, as we have seen it now many times, hopefully. And again, we're going to do our description of a stationary medium, so ddt equals to 0. And we're going to take that we only have variations along DDC axis, so 1D Cartesian. We could do this generically, you know, it's an extension of what we will do here, but then you already know that the transport equation that we have is mu, the I nu dc equals eta nu for nu I nu. This should hopefully now be familiar. It's the 1D Cartesian, where again, I remember, be aware of the sign here. Here I have not put any, you know, the standard plane parallel approximation we spoke about, where you reverse the axis by introducing the optical depth scale in the other direction. That's not done there. Yeah? We're going to just rearrange this equation a little bit. Writing is that I'm just going to move over I nu there, and then you see that it's eta nu divided by alpha nu, right? Minus mu the I nu dc, and then we have an alpha nu here. Okay. And now we're going to say, okay, we have this diffusion picture, which means that we have to deal with only small deviations from the equilibrium situations. Sort of a requisite here. We will come to exactly what the more precise prerequisite for that this is to hold. You can think of it for now that the optical depth has to be much greater than unity. We will connect this later to the mean free path of photons, which has to be small as compared to the typical length scale over which macroscopic variables such as density, temperature, etc. vary in the system. All right. Small deviations around the equilibrium situations means that, okay, so we know what the equilibrium situation is. We can call this the 0, that I nu 0 is the equilibrium. Then we know that this is just then the Planck function, which was then just the source function, of course, and eta nu alpha nu 0, 0, we can put 0. This was the equilibrium description that we had before. So, okay, to obtain then a first order approximation, we just need to insert that on the right-hand side to get the first linear approximation of this, which, as you can see, is just then B nu minus nu dB nu dC divided by alpha nu. All right. Well, that is our radiative diffusion equation. We're done there. So that was today's class. No. We're going to work with this equation now. Now, of course, you could potentially include higher order terms here. You would just repeat this. You would just take this one now and insert it again. Then you would end up with a second order derivative as a correction, a third order, etc., etc. So what you can see is that essentially we have replaced the linear OD by a gradient in the Planck function. So if we know the behavior of the Planck function at a given frequency, that is if we know the temperature structure, yeah, then we can evaluate this. And then we have our intensity without solving the actual linear ODE for the specific intensity itself. As just a side note, you could continue this and derive a second order as well, huh? By just taking this and then plug it into the original again. Did I get this out right? I need to. So in that case, you would have the second order. Let's see if I can do this. It's actually sort of interesting, so I wanted to do this. Normally don't. Then it would be alpha nu ddc. However, here we would have to have then b nu minus mu d b nu divided by alpha dc, yeah? So the second order, this is just a parenthesis for those who are interested, it's actually then b nu minus mu alpha nu db nu dc plus mu squared alpha nu squared db nu dc2. So you can see that the higher order, the more orders you want to include, the higher orders you get here in mu and in b nu. Now, if you continue this, you could actually do a full Taylor expansion here, you know, all the way to whatever order you want, okay? And the interesting thing is that you would actually find then, hadn't thought about this before, that this one and the next term will of course be mu3, and then mu4, and then so forth. But of course, if you think about what I'm doing next, you will see that all higher orders, for some, they will cancel and not. So that all the even will cancel and all the uneven will cancel. Yeah? So, but there's no real point in doing that. This is the standard first order diffusion equation that we're going to use. Okay. So let's look at some quantities then of this and what it actually means to have these type of small deviations. We see that we have a deviation directly that depends on the gradient of the equilibrium value, which in this case is the Planck function. And it has the opacity, it has the angle there, which is a geometric effect, right? And it has the extinction coefficient, of course, there. We can start with the energy density, right? The energy density we know now very well. It's just 1 over c. I knew the omega, where I will just now keep the frequency, so we don't frequency integrate at this moment, okay? So that's just 1 over c then. There's only a mu there, so we can directly take out the 2 pi. Then we have mu minus 1 to 1, right? And then b nu minus mu, the b nu, this alpha nu, d mu. Okay. So here I have to make another remark. And that is that the rest of the results that I obtain now actually relies on that I can assume that the extinction coefficient here is angle independent. That is, that it's isotropic. Okay? Now, when is this the case? Well, it is the case in, when, for example, when we have the static medium situation, that is that the bulk flow is not moving, the bulk velocity is 0. Okay? If we have a bulk velocity, which for example is often the case in the type of outflowing stellar winds that I study a lot, then this has an angle dependence in it. So then again, in order for this to hold, you have to transform yourself into the frame co-moving with the fluid, the Lagrangian frame, if you will. All right? Otherwise, you have to deal with that annoying angle dependence. But like I already said when we introduced the radiative transport equation, we're going to make life easy for us now. Just assume that we have a static media so that we can take this out. All right. Let's take this out. What do we see by this equation then? Well, this should be familiar to us now, right? It's more or less the same argument as we have used for a couple of weeks now. There is no angle dependence in B, right? Right? We assume there was no angle dependence in there. Then we have a mu integral here, and that's an uneven power of mu. The interval is even, so that integral will be 0, as I got from the audience. So this one vanished, and the only one we're left with is that. Okay. And B nu is angle independent, as we know. That's the Planck function. So this one is just 4 pi B nu divided by C. Okay? Or if we frequency integrate this now, well, that's sort of a trivial frequency integral, I would hope. It's just 4 pi divided by C, B, which is just 4 pi divided by C, sigma T4 divided by pi, 4 sigma C T4, which we called before A T4. It's the equilibrium value. So the energy density, or the mean intensity, if you prefer to work with that, that's just the first angular moment of the specific intensity, is unchanged in the diffusion approximation. That's the first result. All right. Let's see what we have now. We're going to do this instead of taking the first moment, because that's going to turn out, as you perhaps already anticipate, to be the more complicated one. We're going to take the second moment, the radiation pressure. Okay? The radiation pressure in this situation, we know that it's just the PCC component, yeah, which we just call the radiation pressure. Remember? Yeah? And then we're just going to do the same thing. Okay. So what integral do we have? Well, we have 1c. We can already take out the 2 pi. I hope we can agree on that. The minus 1 to 1. Correct me for all the errors I'm doing now. B nu minus mu, the B nu, the C, we have our alpha nu. But now we have the mu squared, of course, here, and then we have the mu. Okay, we're going to apply the same argument. What happens then? Well, we sort of have one mu there, right? And we have two there, so this cancels again. It's an uneven, right? So we can see where this is going. All the even moments cancel because the integral becomes uneven, this one here, right? We could continue, but I don't know what to call those terms, you know, the third and the fourth and the fifth. Normally we just work until radiation pressure and we close it there. Anywho, now we get 1 over c, 2 pi, b nu we take out, and then there this integral is just mu squared minus 1 to 1, that's mu cubed 3 to 2/3, right? So that's 2/3, so okay. Well, we can just, we see what this is, right? This is just E nu divided by 3, right? Or if we just do the trivial frequency integration again, we get that P equals to E divided by 3, which was again the equilibrium radiation that we had, the same. So then again, also, the second moment, the pressure is not changed in the diffusion approximation. This is, of course, very convenient. All right, well, now we're going to do the first moment. So, we have already said in the beginning of our class that, well, we need some sort of way to get out an energy transport. An energy transport is sort of a flux. So, let's see if actually we're going to find something now for the flux. Because we recall ourselves, what was the flux in the equilibrium situation of a completely isotropic radiation field? The flux was, sorry? 0, indeed, from the audience. Very good. Now we're going to see what we find. Question is, where are we going to do this? Okay, let's hope we remember this relation. If we don't, you have it in your notes, so that's all good. You can help me. All right, so again, we're going to use our previous knowledge, and we're directly going to go to the flux in the c direction, which we denote as deflux. Yes, and all right, so that's the first moment now. But of course, there will be no phi dependence. We have b nu minus mu d b nu dc alpha nu mu d mu. Okay, well, right. So what happens now? Well, it's the first one that's uneven, right? So this one now, because b nu still doesn't have any angle dependence in it, so it will just vanish. Okay? But this one now has one angle dependence there and one there, so that turns into 2. 1 plus 1 is still 2, I hope. Which means that that won't vanish. Again, we're going to rely on that we can pull this outside the angle integral. We get a minus sign there as well, which is sort of important. And then, yeah, the gradient of the Planck function in the c direction, of course, doesn't really have any angle dependence in it. This we have assumed it doesn't. And then we should have something left, right? Yes, we have mu squared, the mu to solve. That's the same as we had before, right? And it came out at 2/3 then, so it should come out as 2/3 now as well. 4/3, and there we have the flux, right? So, you see that this is it, but we know that 4 pi hat 1 over alpha nu, okay, and then we can write this as b nu dt dt dc, because we know at a fixed frequency, the Planck function is just a function of temperature, right? So what do you see here? Well, you see that the flux, the given frequency here, is proportional to negative of the temperature gradient, the transport of heat. Okay? So here we do get a negative flux, provided that we have a temperature gradient. Also important, it's a negative sign, right? So what does this mean? Well, it means that, let's say we have our star again, and then we want to transport energy from the deep layers out to the surface by means of diffusive radiation. Then the flux has to be positive, right? Upwards. What does this mean for the temperature gradient? Well, that has to go in the other direction. So it has to be lower temperature higher up, higher temperature further down. Well, the temperature increases inwards. This is the simplest way we can understand that in the object. In the case that the radiation transports the energy flux outwards. All right. So next thing we're going to do is that we're going to now frequency integrate this, but now this frequency integral is actually not trivial since it involves the opacity, right? And that opacity in general has a strong frequency dependence in it. So we're going to have to be a little bit careful here. We're going to write this as 4 pi 3, the temperature gradient we can take out, right? But the rest has to now remain in. So we get this integral to solve. 1 over alpha nu dB nu dt d nu. Okay? So what can you see from this integral? Well, actually now, the total flux here is transported out, and it of course depends on this frequency integral. But what you can see in terms of the opacity is that this contribution is going to be smaller the higher the opacity. It's an inverse mean, it's a harmonic mean. We can get it. The lower this one is, the higher the contribution. The higher this one is at a given frequency, the lower the contribution. Okay? So this is equivalent to, say, light transport. Say if I have like I have a pond and I'm standing on top, I look down the pond, okay? And then you have a light source coming from beneath, all right? And then you have a muddy pond, so you have this mud spread out over the whole pond, and it's optically thick, so you can't see anything, right? From beneath the pond. But then you take the same amount of mud, and then you squeeze it together and you push it into a corner. Then suddenly, you have the same amount, but you have light escaping from parts of the pond, okay? It's the same amount of mud, but now actually some light escapes through. We call this a porous medium, okay? Now here you can call that it's porous in frequency space. That is, in frequencies where the opacity is lower, more light will slip through, and in frequencies where the opacity is higher, the extinction coefficient is higher, less light will slip through. This leads to effects like if now we think about, okay, but the total radiative flux has to be preserved, it has to go out somewhere, then this leads to effects like blocking of light in certain frequency band and redistribution to other frequency bands. So, for example, if you work like I do in stellar atmosphere, we have the phenomena of line blocking. That is, We have spectral lines with very high opacities in the ultraviolet part of regions, blocking a lot of the light and then getting redistributed perhaps in the infrared where the general opacity is lower. Okay, so it's just a redistribution there. Now, often you will find this defined as in a harmonic mean called the Rosseland mean opacity. Okay, so that Rosseland mean opacity is just this one written in this form, 1 over alpha r, which is Rosseland, which you often see as this quantity, kappa r times rho, I will on, and that is just then the frequency integral here of 1 over alpha nu, or we can call it then directly kappa nu, dB nu dt, d nu, and then in the denominator you just have this one. Okay? Now this one, of course, is then just dB dt, and that we can solve, right? So this now lends ourselves, before we put down the final description for the flux here, we have introduced this quantity kappa here. That is, we have written the extinction coefficient, in this case the Rosseland, but we could do it also frequency by frequency. That is, write alpha nu as kappa nu times rho, where this is often called the opacity. It is the mass absorption coefficient. We can look at the units it has to have. This was 1 over centimeters, right? This was 1 over centimeters in our lovely CDS units. This is the mass density now. So that is grams per centimeters cubed. So you can see that this must then have centimeters squared per gram, this kappa quantity, or the opacity or mass absorption coefficient. This was then aside. All right, so now we can write this indeed as our Fc is minus 4 pi third dt dc, and then we have the b dt here, and we should have 1 over kappa Ross times the mass density. Yes, please.
In the course, you just put 1 over kappa r is equal to that fraction with the integrals. You drop like the rho that goes with.
Yes. Yes. My apologies. Of course, this is. I was just reminded by the audience that, you know, I have a definition, alternative, a unit problem here, because I said that this was 1 over kappa rho, and that's correct, but then I can't put the equality sign here. I have to actually define this. We're going to do this. Very good observation. This is what I mean that we learn together. Kappa rho like this, and then you have to define kappa rho like that. Okay, and now we see. Now analogously, you could put alpha Rosseland there. Then you would have to have alpha nu there, right? Okay, very good. Okay. All right, so here we have our expression for the flux. dt dB dt 1 over kappa rho kappa Ross times rho. Okay, so we can choose to write this down in various descriptions. Hopefully they're clear from this. But often you will see this directly in terms of the temperature gradient. Yeah? So then we just need to evaluate this, which, you know, is not very difficult. I would hope for T3 by pi, right? So in terms of the temperature gradient, you will get 16 sigma divided by 3 T3 1 over a rho there dt dc, which you sometimes, it's a minus sign, will see as k r dt dc, where this is then called the radiative conductivity. Yeah? This constant in front here. If you prefer to put this as the temperature gradient, right? Now, we could also put this in terms of the energy, right? And then we will again use that we know what the energy is. It is 4 pi divided by c times the Planck function, because we already said that, okay, in the diffusion approximation, the energy density is not changed. That's its equilibrium value. So we know this. So then we can put this term also in terms of the energy gradient. So this will just be dB dc. So that is just then a c or pi a rho. That is just minus c divided by 3 kappa rho, yeah, times the E dc, okay, which I now will write as CL divided by 3 dE dc. And confusingly, sometimes you will also hear this as a radiative conductivity. So just keep your... It is always clear from the context whether we're talking about this form or this form, right? One just have to know what it is that we're doing. And the little L here that I've introduced is 1 over, in this case, the Rosseland, right? But we can also do that frequency by frequency, 1 kappa nu rho, or 1 over alpha nu, which we know is the equivalent, right? Now this is indeed then what we call the mean free path of photons. And after a break now, we will discuss how this concept of the mean free path of photons, together with a random walk of photons, you know, the drunkard's walk, if you will, like this, yeah, can be directly connected to the diffusion approximation here, and see if we can learn and gain some more insights from that. All right. Take a break. Okay, so we'll start again. And we're discussing the radiative diffusion approximation. Now, so before the break, we started from our standard radiative transfer equation that we've been discussing for a couple of weeks now, using the intensity description. And then we developed the diffusion approximation from that, essentially coming to the flux, which is the important quantity that, as compared to the equilibrium solution, is changed. The energy density, the pressure was the same. Yeah. Okay. Now the thing with the diffusion approximation is that it's actually quite, in that sense, broad, because it applies in a lot of different situations across physics. And what we're essentially doing here now is a diffusion approximation for photons. You also are probably aware of the so-called heat equation for matter. You know, when you classically in your course of PDEs or mathematical physics, you have your rod, and then heat is transported from the hot to the cool end, and that's described by the so-called heat equation, which is the diffusion equation, right? You can also think about your perfume bottle. That's another very classical example. Or the Brownian motion. You know, you have your perfume bottle, and then you have molecular diffusion. You squeeze a little bit out, and the molecules are then diffused out. Okay. A lot of these type of examples. There is also a bunch of others. I just mentioned a few random ones here. And we're dealing with essentially diffusion of photons. Now, we had this one, right? Where I said this was essentially this, and then the energy gradient. And this L, which was 1 over alpha nu, or kappa nu rho, is the mean free path. And we're going to go into a little bit what we mean by that now, and how we can connect this to actually a random walk of photons. So we're going to take a slightly different approach then. Look at the little plate here, okay? And then we have opaque absorbers. You can call them atoms. Small atoms here, each which has some sort of cross-section area, sigma. Okay? And they then cover a fraction of this area which I draw, tackled here, say delta A, which then is sigma times the number of, well, absorbers in this case. And they cover then a fraction of the total area A. Okay, we're going to put the little dl here, or the little ds here again, inside, so we can put the ds there and the ds there, and then we see that we can write this also as sigma times the number density ds. Okay, and then we put a beam of radiation here with incoming, and then we ask ourselves how much is going to be absorbed, how much is going to be blocked by this. They're each opaque. That's the assumption that we make here, right? Duk, then we get absorbed or blocked. Yeah, and then of course that's going to be the fractional here. So the fractional diminishing of, if we put this in our intensity, is going to be this, but it's a diminishing, so it's just minus this, right? Minus sigma n ds. Or if we just integrate up this, I nu e to the minus integral ds. But this integral we should recognize. We have had it before. We called it then the optical depth. This was the extinction of light that we had. So this is an alternative definition of optical depth. That's the integral of the cross-section times the number density integrated over your path there. And of course, in general, these little absorbers here, they could, of course, depending on the frequency, we could have a different sort of cross-section, right? So generally speaking, we would also here have to have some sort of frequency dependence in it, right? Now, previously we wrote this as alpha nu ds, right? So we can already from this here see that alpha nu could also be described as sigma nu times n, and we had it before also, before the break, we did this one, right? So let's just check the units. We checked this one already. We know this has 1 over centimeters. A cross section, of course, has centimeters squared. Number density 1 over centimeters cubed. So that all checks out. All good. We're happy with that. Okay? So from this also then, there is a variety of ways which we could connect this to the mean free path. Probably the simplest way is to say that, okay, the typical mean free path, the average distance that the ray here will travel before it gets blocked, in this case, before it hits one of these atomic absorbers, is just when this area there reaches unity, the corresponding distance. So that would just be then sigma n L, we call it mean free path, is just unity. So this is how we see that the mean free path is just 1 over sigma, sigma nu, times the number density, if we want to put the new indices there. Because, of course, this can also then be frequency dependent. Alternatively, we can also see that, okay, if we have a homogeneous medium, that is that the extinction does not vary with location. Remember, we started our explanation with the homogeneous slab. Then we could say that, all right, tau nu was alpha nu ds, which then is just alpha nu times L, where L was the length of the slab. In the case that was homogeneous, written here, this is sigma nu times L. But of course, if we now identify this length with the mean free path, we see that it's sigma nu times mean free path, and that's just unity. So in this case, the mean free path is indeed equivalent of an optical depth of unity for a homogeneous medium. So in this way, we could also write then the optical depth, characteristic optical depth as the total length of the slab, not saying now that it's equal to mean free path divided by mean free path. So in that sense, the optical depth is a measurement on how far we traverse as compared to the typical mean free path of a photon, right? Now recall yourself is that why it is that over such a mean free path, the intensity only decreases by a factor of E. It doesn't go to 0, right? It would go to 0 if all of these atomic absorbers were aligned, because then when the fractional area equal that, well, they would all be blocked, right? Yeah. But the fact is that they're not. So they're spread out here, and then they can overlap, which means that one can actually hide the other one. And that's the whole reason why we get this transparency effect, that once we have reached one mean free path, we're still not at the intensity of 0. We have only decreased a factor of E. And that's just a consequence of this, that, yeah, we have assumed our atomic absorbers like this, but one can hide the other one there, which means that we still get some transparency effects. Again, remind yourself is that what we have neglected also in this picture is, of course, that you also have sources here. And that's the source function thing that we have added in our description of intensity before. Okay. Now, we're going to explore this mean free path a little bit. And its connection. So we're going to take this away. And it's easier here to do it with an example. Now, I started, of course, the diffusion in the previous class discussing optically-thick media, and I took the star as an example. We could have also taken a very optically thick accretion disk or the other astrophysical media of interest, right? But, of course, the sun is just there, so it's easy to take it as an example, so we're going to do that again. All right, and then we're into the, okay, but what is this mean free path of a photon now, right? Typically in the sun. And to do that, it turns out that this description with kappa and rho is a convenient way because we can do a simple order of magnitude estimate. This is not exact, it's just to give you a feeling for it. Okay? So for that we need some sort of average density of the sun, so we can just take that the average density of the sun times the volume of the sun. It's a sphere, right, with some sort of radius. That's going to be the mass of the sun, okay? So in this sense, the order of magnitude average density of the sun is just its mass divided by its radius cubed and some numerical factors of order unity, or a little bit more or a little bit less, yeah? This is 2 times 10 to the 33 grams. If I'm wrong, somebody correct me. This is 10 to the 10 centimeters, I think, like this. The point of this, of course, this is 30, and there you get another 2. So this is just on the order of 1 centimeter, a little bit more perhaps. But we also had some 4 factors there, which we neglected. 1 grams per centimeter cubed, right? Now, kappa nu, we would have to calculate, so I'm just going to give you that for now, right? The reason why kappa nu is a convenient, one of the reasons it's a convenient measurement of opacity, right, is that, well, a typical value here would be 1 centimeter squared per gram, okay? That's not the case for extinction, for example, alpha. So the mean free path then becomes, well, you know, 1 over 1 times 1 in CDS units. So on the order of 1 centimeter. Again, this is an order of magnitude estimate. It's not intended to be precise. It's just intended to show you that on average, the mean free path inside the sun of a photon is really, 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 really low. It's actually, if you go to the core, because the density increases so rapidly toward the core in the sun, it's actually even lower close to the core. Yeah? So this is a little bit an overestimate. So, but then you can think, okay, we had this diffusion process, right, of energy, and now we're again going to assume that that's how photons come through this whole region, released from deep inside the sun, and then they're going to diffuse outwards till they reach this boundary layer, and then they're going to escape to us, and they're going to reach us 8 minutes later, because that's how long it takes for them in free streaming from the surface of the sun to us here on Earth. But then what's going to happen, of course, is that they're going to be constantly absorbed, re-emitted, scattered around, etc., all with like a distance of 1 centimeter. Yeah? But the radius of the sun is very, very big. Huh? So it's going to be something like this. I can't. And then, you know, some are going to be scattered down there, and another one is going to be, yeah, and they're going to have a hard time getting their way up. Huh? And then perhaps, yeah, okay, and then it becomes longer and longer, and then it escapes. And some of them eventually, they're going to escape. Okay, this is what we call a random walk, a Rankin's walk, and you can ask yourself, but how on earth do they get out at all if the mean free path is so short? How can this happen? Well, think about it in this way. All right, if I'm now standing here and I do the Drunkard's walk, yeah, I tilt one step on this, and I can only tilt in this direction now. That's going to be easiest, right? I tilt in this, and then it's 50-50 going there and there, right? Then it's here, and then I can tilt there, and then 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 there, and soon I'm going to be out of sight here, right? Now soon I'm out of camera in the video recording. In the classroom you can still see me, yeah? But I'm actually, if we think about this as the edge, then I'm now out of the edge, right? The thing is that when you describe this process, you can also do it, you know, if you're I don't know, if you've been at Audemarkt and you're going to walk randomly to the classroom on a Friday morning or something like that, then you can say, what's the probability of me actually in a certain amount of time hitting the classroom? Well, it's not so high, because then you, of course, have the two-dimensional surface. But if we only calculate the distance, then you can sort of say tilt the distance, and then if you're standing at Audemarkt, you can ask yourself, okay, after a certain amount of time, where is my friend? Will she or he be at the center, or will they more likely have tilted toward one or the other way? Okay? This is the so-called random walk. And to make it easy for us, we can just say that in this case, this is what we're interested in, we're going to either take one step up or one step down in the c direction. Okay? So either one step, which then is with L plus, or L up, or one L down. Okay. And then the average is not a good measure, because the average will come out as 0, right? But we know that the likelihood that we're actually exactly there is not going to be high. Yeah? We're going to be tilted this and we're going to be tilted that. And the whole idea here is that for some of them, we're getting so tilted that we actually reach the boundary layer and we can escape. Right? And the good measurement for this is the root mean squared. So in this case then, we can say that at the nth, yeah, we have two possibilities. We're either at dn minus 1, right, plus L, okay, or we have the possibility B, where we're at dn minus 1 minus L. Those are the only two, right? And they're equally probable. We don't have a higher probability to tilt one way than the other in this example here. Then if we now calculate the mean, then we can see that this is just then going to be the NA squared plus, this is the root mean squared, right? Divided by 2, which is then just the n minus 1 plus L2 plus, the n minus 1 minus L squared, and then we're going to have to divide this by a factor of 2, right? Now, you can just look at this and you can see, okay, but that's neat because the cross terms, they're going to cancel. Yeah? And then we're going to get 2 of these out, and that's going to cancel the factor of 2. So we're ending up with dn minus 1 plus L squared. Okay, well, that's interesting, because we can now just put it in this way. If we start at dn0 squared, we say that to be 0, then we see that dn1 squared is just L squared, right? Oh, no, the the 1 squared. The 2 squared is just then 2L squared, and the 3 squared is just 3L squared, and so forth, until the n squared is just going to be n times L squared. So the root mean square average, the n squared, is just going to be square root of n times L, where L is your mean free path. And this is, of course, the square root of n law that you may or may not have seen in your statistics course. So did this have anything to do now with photons escaping the sun? Let us think a little bit about that, because I'm pretty sure it did. Okay, so that's a good measurement on how far we are now from the core. So if we now have again our random walker, and we're interested in then reaching the boundary layer here, which is some distance d, then we want that distance d now to equal this square root of n times L, because we want it to be the root mean square distance. Now, another way to say this is that if we have n number of scatterings, absorption, re-emissions, that's going to be d squared divided by L squared. Okay. So now, what time can we associate with this? Well, that's a random walk time. Well, that's sort of, if we now again put ourselves into this, what is the random walk time? Well, in one of this, it takes L, right? So L times the number n, that's going to be the time times the speed of light c, because that's how it goes in one of these. So that's just going to be L times n. So the random walk time in this case is just going to be Ln divided by c, or if we put it into this, we can see that it is d divided by c times d divided by L. Or if we put this in the, for the sun, it would be the radius of the sun divided by c times the radius divided by L. Now, the first here we recognize as the free flight time, right? And the second term is the enhancement factor. The free flight time here is how long time it would take the photon if it were just freely escaping from where it was initially created, released, and then just out here, right? That's the free flight time. We can calculate this for the sun in a simple way. That's just the radius, which we know is 7 times 10 to the 10 centimeters. The speed of light we know is 3 times 10 centimeters per second. So this is just on the order of 2 seconds. So it would take the photon roughly 2 seconds if it were free streaming. Now let's see how long time roughly it would take for it to actually diffuse out. So that's going to be times this enhancement factor. We already calculated this to be on the order of unity. The radius, the order of unity in the sense that it was a centimeter. The radius of the sun we have there. So this is enhanced by a factor of roughly 10 to the 11. So this is on the order of 10 to the 11 seconds, which is on the order of 10 to the 4 years. Again, these are order of magnitude estimates. You could do a more detailed calculation of this, come out a little bit higher. The point is that it takes thousands and thousands of years for when the energy is released down in the sun, diffuse outward to the surface, and then it goes out by means of this random walk process. Yeah? I am trying to avoid to say that it is the photons that are created in the core here and then they're scattered around and then escaping, because technically it's not the same photons, right? But it is a useful picture to have. Now, a further useful concept here is that you can see, well, so this random walk time that you have is roughly the free time, and then it's enhanced by this factor, but this factor we already have. We associated this with what? Just a few minutes ago. The scale of the system divided by the mean free path was roughly the optical depth. Go back a few minutes, and then you see that this is on the order of the free flight time times the optical depth of the system. So in other words, we can estimate the optical depth of the sun to be, well, 10 to the 11. And that's a pretty opaque medium indeed. All right, so finally then, I wanted to take this back now to our discussion of diffusion and the heat equation for radiation. So again, I'm going to repeat this. We had the random walk time, which was roughly the free flight time times the optical depth, where we had the optical depth to be on the order of the scale of the system, call it R, divided by the mean free path, L, right? And free flight then is, of course, R divided by c, speed of light c. We're working with photons. We also had that the diffusion coefficient was Lc divided by 3. We saw that before the break. Okay, so now we're going to take this as to the continuum limit, we can call it. So let's say we have our number density now of photons at some time t plus delta t, and it's at the c. And this has been released at some earlier time t, and at some position c minus delta c, okay? So again now, we assume that this delta z is small enough that the photon density doesn't change along that time scale. Again, this is a prerequisite for the diffusion to be valid. So then we can actually write this as t plus delta t c as approximately then phi t c minus delta c. It is not exchanged. And then we can Taylor expand this in C and see what we get. The phi dc delta C. And now actually I have to keep the second term. This is a interesting curiosity, perhaps. Okay, we can now look at this expression. We can divide it through by a delta t, which would be the mean free path, divided by c, right? And then we can put it on differential to get the phi dt approximately minus phi dc delta c divided by delta t plus now the 2 phi c squared delta c squared divided by delta t, okay? So now we're going to do the addition, actually, that instead of just having our random walkers moving upward and downward one step, they can actually move in 3D space. So then we know that the position displacement in the c direction is L, the mean free path, but times the angle, mu. Okay? And then we have to average this over all angles. So we have to take the average there, and we have to take the average there. I forgot a 2 there. Thank you. Okay? Now, the neat thing is that these averages, they will be very familiar to us, right? That's L. And then we have mu minus 1 to 1. Mu the mu. Well, we know how this comes out. This we have done 100 times now, I think. And delta c squared, yeah, that's going to be then L squared. Mu minus 1, 1, mu squared the mu. Well, we have also done this a bunch of times. So this is the 2/3 factor that comes out from this consideration instead of just up and down here. Okay. So the first term vanishes. We can use the energy as h nu times the photon density to write this now as the E dt. The first term vanishes. The second term, we have this, and we're going to do this now. In our head, we have L squared, and then we have a 2, and then we have divided by 2, so those cancel. We get a third down there, right? But the delta t there, we have, that's just the photon mean free path, L divided by c, so c comes up. 1L stays, and we have divided by 3. So this just becomes L, C divided by 3. The 2E, dc2. And what do we recognize this as? The diffusion coefficient. So, now this is in a form equivalent to the standard heat equation of matter. We will discuss how it connects to the radiation energy equation in the next lecture. Right? For now, stay with me. And then we saw, okay, well, it's a little bit, but yeah, well, we had previously, remember that the flux in the c direction was negative fusion d E dc, right? So if we just look at this now and we plug this in, then we see that indeed this is that the E dt equals to minus then the Fc dc, which is then how You see how the flux related to the energy, and then you come to your heat equation. I do already now make a note that complicating factors here are the sources and sinks on the right-hand side. That is, if we're not completely in equilibrium with the emission and absorption. Plus, we can also have advection terms, which produces enthalpy, okay? Something can be complicating factors here. But what is neat with this is that we can actually, now we have identified this from the continuum limit. We had the heat equation, but we can then use this to analyze this expression in the same way as we analyze our heat equation in our course of PDEs. Okay? So we know from that if we have something where the energy is described by some constant times the delta function at C equals to 0. And then we solve the heat equation, this equation. For that, we know the solution to be a function of t, and I have to look it up now. This is not for this course to solve it here. This is something you will do at another place, in another time, for the t, so that you can see that the sigma squared here, which is of course your root mean squared of this Gaussian, is just 2 dt, so that your diffusion time is going to, in this case, if we put it back to our star, where this was then d squared, right? This was the d squared, or r squared, as we called it in this case. Our diffusion time would just be r squared divided by 2 times the diffusion coefficient. And the diffusion coefficient, we know what it is now. It's LC divided by 3. So here we get 3/2 d, or r, I called it now L, r divided by c. So we see that again, we have the free flight time scale here. We have the r over L here. And then we have a factor of 3 to 2. And that's just the correction factor that we obtained here for actually introducing the tilt. That we could not just go up and down, but we could move in 3-dimensional space. So that just enhances the diffusion time by, in this case, 3/2 as compared to the 1-dimensional case here, which is also easy to understand, because if you can tilt it, you know, the average will be a little bit lower. Okay? But this is then how you can immediately see that this is indeed equal to the random walk time as we had before. Now, you can use this and then see how really what is happening here is that you have a bunch of photons released, and they're essentially over time spread out like this in space, and then eventually some of them reaches the surface in this picture and then escape. Most of them will not. It's just the ones in the tail that actually will escape, right? And it happens on these time scales here. And furthermore, if you actually now were to just integrate this over the full space, you will see that what gets out is the constant here. That is, that energy is actually preserved totally by this process. It's just transported, and that's why we call it the radiative diffusion and the transport of energy from the deep interior of, say, your accretion disk or a star out to the surface. All right, that was it.